Thank you, Ingo. Welcome, everyone. Hope you had a good lunch. Not too tired yet. This talk is going to be a bit packed, I think, yet hopefully it's going to be useful for you. Personally, I have high hopes for that because I think this talk would have been extremely valuable for me 1 year ago because I had to learn a ton of things about Perf. So what is Perf? Perf is a benchmarking, profiling, and tracing tool written by Linux kernel developers. Quick show of hands, who has tried to use it, or actually, who stopped using it after like 5 minutes? Okay, this talk is for you, definitely. And I think for those of you who still use it, I bet there will be some tricks in this talk for how you can use Perf to even greater effect. On the agenda today is first a bit of setup, because many people try to use Perf in the least optimal way, namely they simply download it from their package manager and start using it and realize it's crappy and then uninstall it again. I'll first start with that to get you all to the same level that I'm at. And then we will be covering benchmarking, profiling, tracing, and then finish off with a bit of scripting. So let's start with the setup. Linux Perf is kind of picky. You need to understand how it's working to figure out that you first must make sure that your hardware actually supports running Perf in the best way possible. Once you have that, you actually need to compile the Linux kernel in a good way. Thankfully, nowadays, that's usually not a big problem, but I'll cover that a bit. And once you have that, please don't use Perf from your distribution. Usually it's really, really horribly outdated compared to what you can get from Git. And actually compiling the user space part from Perf is super trivial and gives you lots and lots of nice features. And once we have that, I will cover quickly cross-compiling because, again, quick show of hands, who's using Perf on embedded devices? A few people raised their hands. For me, I actually like using Intel's vTune commercial profiler a lot on desktop, but on ARM hardware, my hands are tied. I don't have any alternative to Linux Perf. So most of the stuff I'll present here is mostly driven by the fact that on embedded I have to use it, and I try to figure out how to make sense of the data given to me. So cross-compiling is very important, and finally, to actually use some of the tools, you need proper permissions, and I will cover that as well. Okay, let's start off with the hardware part. You need hardware that has hardware performance counters for at least the sampling profiler to work correctly. And if you Google for that on Wiki, you will see, for example, that most ARM CPUs have a few hardware counters, like 2 or 4 of them that Perf can leverage. And these then can be used, for example, to count cycles, count instructions, count cache misses, count branches and branch misses, and all things. It's pretty powerful. But you need to be aware of the limitations. So some cheap ARM CPUs only have 2 hardware counters. So you cannot measure branches, branch misses, cycles, and instructions at the same time. Or if you do, you run into trouble with like software muxing in between and things like that. So really first check your hardware, what are the capabilities of it, and then configure Perf to run properly. Because otherwise you will get garbage results or no results at all, which can happen on IMX6 hardware, where some of the stuff is simply broken and it won't work at all properly. I will cover questions later on, please, okay? So once you have that set up, hopefully on the hardware side, Perf should be able to run. And then you need to configure your kernel if you compile it yourself, which is usually the case if you have a build root or a Yocto setup. But if you just run it on a desktop or if you have a pre-existing SDK, simply grab into your config and see whether you have the Perf events enabled and whether you can access the user stack dumps and things like that. It's as easy as that to get a quick check whether it could work at all. And once you have that, actually the Linux kernel version doesn't matter that much. I would say since Linux 3.7, it works mostly pretty well. And all the rest is just then actually analyzing the data in user space. So recording data happens in the kernel, but that actually works quite well. What is not so nice still is the user space. So analyzing the data that was recorded. And for that, I really, really recommend you compile perf from sources. There are two options. In this talk here, I will present some features that are not yet upstream. I actually started contributing to perf to improve some of the ways to make it more usable. I added some new features there, which I will show here. So if you want to reproduce my results, use my fork of the Linux tree, or I hope to eventually get all of them integrated, and some are upstream already. And Arnaldo's Acme branch is like the go-to gold standard in my opinion. He is the maintainer from Perf, and his Perf core branch has all the latest and greatest in Perf. So this is usually what I work on. And to actually build Perf, it's trivial. Most of the time you simply go to your Linux checkout, enter the tools perf subdirectory and run make in there. Do make sure, don't set cc to clang. It will fail to compile and you will wonder what's going on. Simply export cc to gcc and it will work. Just run make and you get a binary called perf in your current directory and you can run that as is, as a drop-in replacement for the one you get from distribution. It's really, really trivial. What's not so trivial is getting all the dependencies. Thankfully there you can actually rely on your distribution or enable them in build-root or Yocto. This is actually being outputted at the beginning of the make step in perf. And as you can see, there are tons of dependencies, and some of them you can, some of them you must really support. I added comments behind, so definitely you need the dwarf libs and elf utils and bin utils utilities for symbol, syscall, and unwinding support. They are really crucial. If you want scripting, you also need the development packages for Perl and or Python, depending on what you want. And the libouted one is interesting if you want to use perf trace. If you don't have that, it won't work. And libslang, which is a really esoteric old library. The website is funny. I recommend you have a look at that. It's actually still being used to get the command line graphical user face up and running. And libcrypto is used for probe points, so jitting and inserting inserting trace points into your code at runtime, if you want that. Okay, now we know how to compile it on a desktop, but how do we do it on embedded platforms? Usually we need to cross-compile there. And that is actually not that hard. I simply didn't know how to do it. I asked the kernel developers, how do you use your tool and cross-compile it? And this one line up here is the de facto way to do it. Just run make, set the arch and the cross-compile prefix. So in this case, you have a SDK in your path with GCC called arch64-linux-gnu-gcc, right? It just prepends the cross-compile to all the tools. And then it should work. But usually it doesn't. At least that was my experience with it. There are some pitfalls if you run into issues. First of all, if you have a broken SDK, which sometimes happens, we have lots of these at KDAP. Customers give us their SDK, and they have a CC environment variable that not only contains the name of the compiler, but also of, for example, the sysroot flag. And the build system in the kernel will not understand that and simply omits all the extra flags inside CC, and nothing will compile. So first make sure CC only has the single binary name. And if you want to pass additional flags, it's not sufficient to set C flags, you must define extra underscore C flags for some reason. And the prefix path that you can configure, maybe it contains hand-compiled libelf utils or the libbin utils or stuff like that. For that to be picked up properly, it's not enough to set the prefix path, but you also need to pass the -i and -l flags to the extra C flags. And when you still have issues with dependencies not being picked up, make will be silent. It will simply tell you it didn't find the dependency, but doesn't tell you why it failed or what happened, right? And there's a folder called build next to the perf folder. And in there is a feature folder, and in there are all the feature tests. And if something failed, there's a test dash and the name of the feature, .make.output. Look at these files, because they actually tell you what happened. So maybe it didn't find libunwind's development headers or something like that, right? And from there, then you can actually work on making it run. Okay, cool. Now you have a perf binary. And you run it, and then you realize you get an error message. Actually, older perf versions simply told you like error 51, I cannot work. And if you're not a kernel developer, you couldn't parse the error message at all. They finally, over the last years, started to improve on that and tremendously improved the usability by actually printing good error messages, telling you what to do. I have this little script up here on the slide that sets a couple of things so perf works. Most notably, you need to read access to the debug pseudo file system. And if you intend to use tracing capabilities, you also need read access to the tracing file tree system. And these are the first two commands. The commands below that simply increase your access rights to some more things, like being able to read and write uprobe events, so user probes, and things like that. If something is not working, this is usually the reason why. Like you need to set these commands or run perf as super user or root, but usually that's a bad idea as a development or as a developer. I rather prefer running everything as my own user. Okay, cool. Now we want to start using perf. So one of the first really tremendously useful things that perf is offering is benchmarking utilities. But benchmarking has to be done properly. I mean, there are many tools, for example, qtestlib offering you a benchmark suite. But benchmarking has to be a scientific process. First, like measure something, create a baseline, remember how long did it take, and then repeat it, and then compare, and you need to take variance into account, like maybe you run it once and then the second time and there's a change in cycles, but do you actually know whether the difference is significant or not? Is it like within the variance interval or not? You need to benchmark, or you need to measure these things. And comparing before and after is also extremely important. And perfstat allows most of that. So, perfstat is the first example I will show you. You can pass it a -r and a number, and it will repeat the command in a certain amount of time. And I can tell it to output I can tell it to write the output to a file. And then behind the dashes, I have my command. It's as simple as that, usually. And if I look at the output, I see that perf is actually outputting a ton of information to me. I see the task clock, so how much CPU was utilized. Imagine you run a multi-threaded application, or something that is supposed to be multi-threaded, and you see it's just using one CPU or something, like less than the number of cores you were expecting it to use. You are instantly seeing, okay, I'm suffering from lock contention or something like that. I see number of context switches in CPU migrations, which are usually extremely costly. Same for page faults, which often trigger context switches in return, and then you have lots of latency in your application. Then you have cycles, instructions, branches, and branch misses. And this example here is actually triggering a lot of branch misses, so 25% of the overall number of branches, which is really terrible, but I deliberately wrote bad code here to show this is working. And at the end, it actually shows you the total time that was elapsed. All of these numbers are related in some sense. Page faults will increase the number of time, but won't actually increase cycle counts. Do note that I actually have modifiers here, these :use. I can limit or I can tell Perf to look only at certain events and also split between kernel cost and user space cost. So I can measure only cycles spent in your driver inside the kernel, and I can only measure the stuff that is happening inside your application, actually. If you look at the man page for Perf lids, actually most of the man pages are pretty good. You can see what you can use as modifier. One example here would be, let's show that quickly. If I just run it as is, I get the output, and by default it will only look at user space cycles, and I can say -e cycles u and -e cycles k, and oh, that doesn't make any sense. Interesting. Okay, that's another bug. Welcome to Perf. It makes no sense to modify to look at kernel events in user space. So of course it measures 0 here. Should have tested that one earlier. Or maybe I should look at the slide. So probably the syntax is different. Yeah, let's try that. Maybe that works. No. Okay, live demo issues. In principle, this should work. Apparently, my Perf doesn't like what I'm trying to show here. It prepends both the user space limitation and the kernel filter. So let's redo that. So if I do that, I actually should see first cycles only in kernel space without the U behind it, because combination of both makes no sense. These things will happen to you when you use Perf. So maybe it's good that I run into these kind of issues, because Perf has these kind of strange limitations sometimes. Usability is not the best. But in principle, it has the ability to do all these things. It's just, yeah, a bit awkward sometimes. Now, I mentioned Perf list already. Its man page will tell you the different modifiers you can pass and to increase precision, for example, for the cycle counters to reduce skid. But it also tells you the different hardware events you could measure. And this is really just an excerpt. If you ran my Perf initializer to increase your leverage, your writes, so this is with normal writes, I get 86 events that are accessible to me. Already quite a few. But if I run my little shell script, so this one with which extends my user rights, and I run perf list again, I now have access to 1,629 events that I could use. And this is mostly trace points in the kernel, but some of them are really, really, really useful, like the scheduler statistics, which give me insights into how long and when is my application sleeping or running or actually waiting for I/O to be delivered. I get access to all the syscalls, so this is really, really powerful. If you use qtestlib, you can actually leverage perf inside qtestlib. So without any kind of recompilation, you can just run your qtestlib benchmark with the -perf command line switch, and it will not use time, but instead the CPU cycle counter by default. There is a big caveat though. By default, it will set the iteration counter to 1 and only repeat your benchmark once. This is a very bad idea because cycle counters will fluctuate. There is a variance there. So you have to manually go down and say, repeat it for, let's say, 100 times and give me the median value back. This is what qtestlib is doing. It gives you the median value back. You can also use a different performance counter, like the instruction counter. So you do that by saying -perf counter and then the name of the different event. And suddenly you can measure instructions for your Q benchmarks. Pretty nice. I actually have a work in process patch up for review, and you help welcome there to enable multiple performance counters at the same time for QTestLab benchmarks, which would be extremely nice to have. Imagine enabling both cycles and instructions, and then you can calculate the cycles per instruction required to run your benchmark, and then you can maybe also measure the cache misses and correlate all of these values. There's a slight caveat though. The number of lists and the names of the list, the events, is different from what perf list is returning. So to actually know what you can access, you need to run your benchmark with the -perf counter list argument, and will return a list of available events to you. It is not yet implemented to use trace points with QTestLab. Okay, so this was benchmarking, right? We can run perf multiple times, have a look at the variance. Let me do that again. So perf start, repeat it 5 times, and I decrease the workload of my benchmark. And if I do that, it runs it 5 times and breaks the size of my console, so this is better. And in the last column, it actually shows me the variance, right? It correlates some things, like it actually measures the instructions per cycle. So this benchmark is pretty nice. It is super scalar, right, in that sense. So very, very useful tool already. Way better than using time for the same purpose. But now we actually want to find where in my code base the slow paths are taken, where are CPU cycles being spent. And not only that, but we may also need to look at where nothing is happening. So a big thing you need to know about perf and how sampling profilers in general work is they will measure when CPU cycles are spent while your application is scheduled. As soon as the kernel schedules your application out, it will stop attributing CPU cycles to your application. But what happens if you call usleep or run into a qmutex log contention is that you will actually be scheduled out. So the CPU cycles won't increase at all. If you just look at the image or at the results of a CPU sampling profiler for cycles, you will miss all the nasty sleeping in your application, which often contribute a lot to the total runtime. And fixing those requires a different configuration for perf to find them. Yeah? So we need to do 2 things, CPU profiling and sleep profiling, and maybe even more. The first nice little tool compared to top is perf-top. So I think everyone knows top, right? It shows me the processes that are running and how much memory and CPU they are using. If I run perf-top, I see not only the applications that are being run, but rather I see symbols in shared objects that consume time. So imagine I am a system developer and I see like, oh yeah, Qt5 core is slow inside operator equals. And actually I have the problem right now that I see only the function name. I don't see the file name. I don't see where it's being called from. So this at most gives me a rough idea of where to spend my time on an application basis, right? But it's not really that helpful. I use it sometimes to get a rough feeling, but rather what you want to do is actually statistical profiling. So who in the audience is using statistical profiling day to day for profiling works? Anyone? A few people are raised there, like just 2 people. Is anyone using instrumentation-based profiling like Colgrint or gprof or something like that instead? Way more people raise their hands. You should rethink what you're doing. Use statistical profiling. Statistical profiling is as the name says, a statistical process. What it does is it looks at your program and is not actually changing how it's running. It rather looks periodically at where your instruction pointer is at. So if you do that often enough, let's say 1,000 times a second, by sheer mathematical logic, you have to find your bottlenecks. Because if something is spending a lot of time, by definition, it has to be on the stack often, right? If it's not there, if the statistical profile is not finding it, then it's not a hot function anyways, and you can ignore it. But the biggest problem people have with statistical profiling is always like, yeah, it's too hand-wavy, maybe it's not accurate enough, maybe I don't find the actual slow path. We are Qt developers, so we are like way up the stack, and usually we are not interested in malloc being slow or even maybe something inside Qt being slow. Rather, we are interested in where we are calling these functions. And for that to work, you need call stack unwinding. And once you do that, statistical profiling becomes immensely useful. So what you do is you have your instruction pointer, and then you unwind the stack to figure out where has this instruction being called from. And to do that, you need some mechanism to actually unwind the stack. And there are at least 3 ways to do that with Perf. The default one is frame pointers. So that's essentially in your current stack frame, you have a frame pointer value that points to the previous frame and so forth, and you can simply follow along and build a nice chain of callers and callees. Awesome. Works super fast, is extremely nice. Big problem is it's disabled by default nowadays, even on 32-bit. If you run an embedded platform and have full control over your system, do enable it back. So pass -f no omit frame pointer everywhere. If you're on a desktop, you can leverage the dwarf debug information. And for that to work, you need, of course, to compile your applications with debug information. And then the dwarf unwinder can kick in. It works. It's actually not that bad performance-wise for like large-scale applications written with Qt, but it has considerable overhead compared to frame pointers. And also the result files will be like 10 times bigger. If you are lucky enough to run one of the latest Intel CPUs, you can also leverage the last branch record for the same purposes that the frame pointer gives you without actually recompiling anything. The last branch record can be configured to essentially store the same information, like this function is calling something else and it's being stored in some specific hardware on the CPU. The problem is the size of this last branch record. Usually it's like, 8 entries, 16 entries, maybe the last CPUs now have 32 entries. So that's a big limitation for the call stack you can get back from Perf. So that helps sometimes to use the LBR, but usually I use dwarf on the desktop and frame pointers on embedded devices. And if I have access to LBR, I'll use it, and later on I'll show a trick what you can do with it as well. Okay, cool. So now we can actually record something. And to do that, you call perf record --call graph and then define the actual unwinding method. So by default, it will try to use fp, the frame pointer. It won't work if you try it that way. Use dwarf and then pass your debuggy, and it will record something. Do note here, it already created some output file with 64 megabytes. If you run the dwarf debugger on a heavily multi-threaded application for a couple of seconds or even minutes, you can easily get hundreds of megabytes of output data back. If you want to, with perf record, you can not only launch a new application, you can also attach to a running application, which is sometimes extremely useful. Like as a KDE developer, maybe Akonadi is acting up again. Hello, Dan. And I want to figure out what's happening there, right? Or maybe it's some plasma-related stuff that happened to me recently. So I don't want to restart anything. I simply attach to the process and see what's happening. And I can actually attach to multiple processes if I want to, and aggregate the data into one result file and compare everything. I can even go that far and profile everything, like the whole system, all CPUs, everything that is happening. And Usually what you want to do then is like, say, I want to measure from now until 5 seconds later, and the de facto way to do that is simply profile sleep, or give sleep as the debug argument, because once that argument stops, the perf recording will stop again as well, right? So this little line here will simply profile the whole system for 5 seconds. Once you have reported something, once you have recorded something, you need to report it. And now the real fun starts, because I think in a few seconds you will realize how utterly terrible perf report really is. So I think I'll start with a little demo here first. I have my Mandelbrot application here, yeah? And this Mandelbrot application also has like a benchmark mode, so I can do something repeatedly, which is nice for actually proving that if I change something, things become better, right? So now I actually know what I want to bench, or what I want to profile. I say perf record call graph dwarf, and then my benchmark, right? And I keep that running, and the overhead is really minimal from perf. Those of you who raised your hands and say they still use callgrant or any kind of other instrumentation-based profiler, you usually incur penalties of like, what, factor 10, factor 100, something like that. Perf has like, what, 10% overhead? So that alone is one of the biggest reasons on why you should be using a sampling profiler. Okay, I recorded it, and now I report. And this is the default you can, is it? Yeah. Yeah. This is the default way that perf will represent the data. It's a lot of stuff, and it's like a strange console application that is not that usable, in my opinion. So we need to figure out what it is presenting you. The first column, the children, will tell you the inclusive cost. The second is the self-cost. So self-cost means when you have a symbol and the sampling pointer was inside that function, it will get a sample for this function and increase the self counter. And then you get stack unwinding, and it will increase the inclusive cost of all the parent functions. Yeah? So by default, what you're looking at here is something like a top-down view of all the functions in your application that have been encountered. So usually main is at the top, and then you can go down and see other functions, and they are children. One thing you will notice is it will output the command name, which for benchmarks like that is pretty useless because I only looked at one command. I know that already. Thanks for wasting my screen space there. Then it will output the shared object, which is actually kind of useful oftentimes to figure out where the symbol is coming from. And finally, the symbol name, so the function name. What I'm missing here is the file name and the line number. It's not there. And also, if I look at the call stack, so pressing enter, I see a second really big problem. We are benchmarking, or we are profiling. So what do we measure? We measure an application that has been compiled with code optimizations enabled. If you try to profile a C++ application in debug mode, don't do it. It's a waste of time. You will see lots and lots of cycles being spent in template code that in reality, once you enable code optimizations, will all be inlined, and it's going to be really fast. But inlining makes perf kind of unusable in some sense, because here in this example, the call stack tells me that I have my main function, and inside my main function I call a hypod function, and in there I call a hypod finite function. Or below that, I call the complex multiplication function. I can show you quickly the source code for my main. It does not call any of these functions. It calls my Mandelbrot function, of course. And in there, I do something with complex numbers, and I also multiply complex numbers here somewhere, like there. But I don't call any of the hypod or multiplication functions directly. So where is this coming from? And perf by default makes it really hard to figure that one out. Thankfully, there are ways to circumvent that. You can, first of all, flip around the report by passing -- no children. It essentially removes the inclusive cost and only shows self cost and then anything calling these functions, which is a way better aggregation mechanism in my opinion, because maybe I call the same function from different places and I want to figure out where this is happening. And once I have done that, I can change the other columns that Perf is using. So with -s, I say I only want the shared symbol name, I want the shared object name, I want the symbol name, and I want the source file and line. So -s DSO, sim, source line. And now finally I get to something that is closer to what I'm looking at. I have my shared object lab Mandelbrot that calls inside main, apparently has lots of cost, but that main is actually inline code. So here we now actually see the effect of the inliner, right? At the right side, source line is telling me Mandelbrot.h line 41 is actually the slow code. But if I look at the call stack, it's still pretty useless. So what I can do now is say -g to configure the call graph, and I need to know that I can pass -g address here. And if I do that, then I actually get line numbers here as well for the files and where they are being called from inside the call stack. So this is, in my opinion, way better from the usability point of view. But do note that it's still not showing inline functions here. So the symbol names are omitted for my draw Mandelbrot function, for example. And I tried to work with upstream to get that information in there because Dwarf has that information. It's simply not shown by the user space perf utility. So I usually flip around things with -- no children to get a bottom-up view, then configure the columns to be shown, and then also enable the source line feature in the backtraces. If you try this on your perf from the distribution you have, it will probably not work. I just recently fixed the bug or found a bug there that broke the address resolution completely in backtraces. Okay. If you don't want to repeat yourself, you can use perf-config to write the configuration once to a file, and then it will work the same way whenever you use perf-report. If you want an even better visualization, I can only urge you to try out flame graphs. So with perfscript report stack collapse or perfscript, and then pipe into perf stack collapse.py, and then into the flame graph perfscript by Brandon Gregg, and saving the output then finally into a SVG file, we can open that in a browser or embed it in this browser presentation and get a nice interactive view of what's going on, and I can zoom in. And the wider something is here, the more often it was on the stack, so more costly it is. If you don't know flame graphs yet, do have a look at that. But again, note how it's missing the inline functions here. So this is really something that must be fixed in perf itself. And I hope to be able to do that eventually. Okay. You can actually use perf also for a bit of QML profiling to breach through the JIT barrier, because usually JIT is going to break your backtraces. They don't embed any frame pointer information inside the JIT code. They also, of course, don't put any debug information in there because it would be simply too costly to do that at runtime. So if you would use perf as is with the -- call graph dwarf on your QML application, you will see the backtrace stop at some address without any information. If you, though, use the LBR, the last branch record, call stack unwinder, you can actually get further. It will not be broken up by the JIT. The thing is, you still get only the raw addresses inside the perf report. And thankfully, there's a feature inside Qt since I think 5.6 or something like that, where you can pass the environment variable qv4 underscore profile underscore write underscore perf underscore map equals 1. And once you do that, perf will, Qt, or Qt declarative, will write the perf map file. So in the lines before, or in the report cases before, perf actually told you it failed to open a -tmp /tmp/perf pit.map file. That's the third line in this output, continuing without symbols. If you export that environment variable, Q declarative will write this file, and perf report can make use of that, and it will translate at least some of the addresses into QML function names. It's a bit, or JavaScript function names. It's a bit, it can be useful. If you want to try it out, I urge you to do it. But I think we have to improve the way the symbols are reported to perf here, and for example, also include file names and line numbers and these kind of things. Okay, this was all about CPU profiling. How do we do off-CPU profiling? So how do we measure something when the scheduler pulls your application and puts it to sleep? Because then the performance monitoring unit will not run or record events for your application. So this is really crucial for you to measure I/O time or sleep time and these kind of things. And thankfully, perf list contained these scheduler statistic events, right? So if you run perf list scatstat, it will output all the stats. The documentation is scarce to non-existing on what they actually mean. From what I gathered, blocked is kind of an aggregation of it's not working. I/O wait is, well, obvious I/O waiting. Runtime is when it's actually doing something, so it's scheduled in and running. Sleeping is when you called sleep and your application was put to sleep. And wait means the scheduler offered you to run, but you're still waiting for a CPU to actually run. And with these, you can build the mouthful of a perf command. So first of all, you need to enable the scheduler statistics. Another thing you need to know that somewhere in Proxys kernel there's a scatstats file since recently. You need to enable that one, otherwise you will not get any of these events. And then you record first, for example, the stat sleep, then also process exit to get notified if something, if your process is being shut down, and then the scheduler switch events, which will give you the call graph to where you actually were put to sleep. So this is the interesting point where you actually call sleep, for example. Once you recorded these things, you can disable the scheduler statistic events again because they slow down your application system a bit, and then inject, or well, perf inject is actually a misnomer. It actually rewrites the perf data file and takes the time between scheduler events and takes this time period then instead of the sample number for reporting purposes. So this is a way to get to know how long I actually waited. And once you did that, I actually have the previous slide in a little script called perf sleep record. I run that on my example, and then afterwards run perf report, and I get the nice report of where I actually call qthread sleep in main.cpp line 10. So this is really, really useful, but it will only find sleeps or mutex log contention and these kind of things. It will not find I/O waits. To do that, you can actually reuse the same script and simply replace the scat.sleep with the scat.io wait trace point, and then you will get I/O wait from it. Okay, cross-machine reporting is also pretty important for developers working on embedded. Either you want to convert from one machine that has the symbols available. In this case, you want to run perf archive on that machine and transfer both the perf.data file and the perf.data.tar.bc2 file, bz2 file that was created by perf archive to your second machine, unpack this archive, which contains the debug symbols, into your home.debug symbol storage, and then run perf report. Works. Usually that's not the case though for different embedded projects where you don't have the symbols on the embedded device, right? You have them in a sysroot on your desktop machine. And if that is the case, you need to simply point perf report via the --symfs flag to the directory where your sysroot is in, and then it can find the symbols from there. Okay, so this was perf record and report. Quite a lot to stomach, I think. Let's quickly dive into tracing now. We can trace syscalls, kernel events, and user-defined trace points. Lots and lots of stuff with perf. Perf top is actually quite helpful here again. You can, for example, specify that you want to be notified about all syscalls that are happening on your machine. And if I do that, I usually use the raw syscall sysenter trace point, and I can see that xorg is triggering tons and tons of syscalls. And if I actually want to figure out what these trace points are, I can use perf trace, and you would get spammed by hundreds and thousands of trace syscalls. Actually, what you are usually interested in is slow syscalls. So you can pass the -- duration equals and then number of milliseconds and get only those syscalls that took longer than, let's say, 100 milliseconds. Usually that's polling, that's fine. It didn't have to do anything, so it waited a long time. But in here, you also see MySQLD waiting on a fast user space mutex for 142 milliseconds, which is probably a very bad sign. You can also use perf trace to aggregate the syscall overhead. So in a multi-threaded or a supposedly multi-threaded application I wrote that is suffering tremendously from log contention, if I trace it and pass -s to get statistics, I see that this code is spending 7.5 seconds in futex. So this is like a really bad sign of log contention. And I get standard deviation and all kinds of interesting numbers fed back to me by perf. With perf trace and some patches that are not yet upstreamed by me, or not yet accepted upstream, that is, you can also use perf inject to, again, attribute the time between trace points to the actual trace events, and then use perf report to get actually the time it was required to see the time it took the different trace syscalls. So I think I have to show that quickly. If I perf trace, wait, what do I do here? Yeah, if I do perf trace record and then I have a tiny example that only sleeps once 1 second, once 100 milliseconds, and once a bit less. And if I report, I get a not that useful report back. Actually, let me... oh, I did not enable... Sorry, I need to enable call graph. And I see not much. Well, I actually see what I want to show here. This example slept a lot, but because it's only 3 syscalls that are sleeping, it is droned in all the other syscalls that are happening. So I can actually run perf inject, as is shown on this slide, to attribute the time it takes for the syscalls, and then perf report will tell me this is the one that is actually costly. And I think I'm running out of time, which is a very pity, because I have more interesting stuff you can do. Perf time chart is then the last thing I will show. Perf time chart allows you to trace the whole applications on your machine for a certain time. And then with Perf timeshot, you can create a SVG file that visualizes what's happening on your CPUs. So you can actually see when is something running. If you see gaps between cores, probably there's like lock contention going on. You can follow along how your application is being migrated between CPUs. You can see when something is waiting or blocked on I/O, and these kind of things are all in here. So that's another very, very useful little tool. And I think I won't have time for scripting. If you have some time, look at my GitHub thingy. I have a call grind converter Python script there with which you can also open perf data files in kcachegrind finally and visualize them with this tool if you are familiar with it. So yeah, thank you.
So we have 10 minutes for questions. If you have a question, raise your hand.
Wolff has a question.
Yeah, I was quite astonished that you actually managed to compile frame pointers into ARM binaries. I would like to know how that works.
You're right. That's actually wrong. When I say frame pointers for ARM, it's a lie. Let me go back. You need unwind tables on ARM. It's pretty much the same thing though. So instead, if you say -fp for perf's purposes, it will use the unwind tables on ARM if they are there. But yeah, it's not frame pointers, it's frame table. Yeah, unwind tables on ARM. You're right.
Okay. And yeah, you don't really need hardware support for Perf, right? You can always use the CPU clock event type. That's a bit expensive, but it works.
So another point is that you can use the time, the CPU time for sampling. That is true. But where do I show Perf list? No, later, sorry. There. I think the true value, like, sure, you can always use the CPU clock. It's not even included in here because, in my opinion, it's the least useful one. It's not that. It's not giving you that much information. Most notably, it's not actually a real wall clock thingy. You know, it's still going to stop once you get scheduled out. So if you want to use a proper profile, if you want to profile something, looking at CPU cycles or ref cycles on the hardware that actually supports it is way more useful, in my opinion. And even it's correct that you don't need hardware support in the CPU. You still need some support. Otherwise, for example, Perf won't work at all on different cores. Like that's what you see on IMX6. There's like errata saying like hardware counters don't work at all. And I'm not sure whether you could use the CPU clock there either.
Oh yeah, you can.
You can? Ah, good to know. Then I have to try that out. Thank you.
And also QML actually compiles frame pointers into the JITted binary. And if you want, I can show you a hack that enables libdw to use them when it cannot unwind any further.
Oh, cool. So the point is, apparently there are frame pointers in QML JIT. Yeah. Cool, good to know. I thought libunwind would make use of that by default.
Nope.
Oh, okay, good to know. Thank you.
Oh,
Are there any more questions? I think we got a few minutes. If not, I'll talk about scripting after all. Ingo, how much time do we have? No more questions? Is everyone using Perf now and will be happy about it? I think, or at least I hope that these slides will also act as a like manual for you to follow along and how to actually use Perf, because oftentimes you need these like really long commands. And remembering them is kind of hard, but it's doable. So if there is still like 5 minutes left, then I will talk quickly about scripting after all. Okay, so there we are, scripting. Scripting is useful if you want more than you get from Perf report, for example. So if you want to write your custom analysis for whatever you recorded, imagine you call Perf to with tons of trace points, and you added static trace points to your binary as well, and you want to correlate that to CPU cycles being spent somewhere. None of the existing tools will be able to do that, but with scripting you can write your own tool to leverage all of that and aggregate the data in a usable way. And if you run perf script as is, it will simply take the perf.data file and convert it in a somewhat limited form to ASCII. So by default it will print every event with the timestamp, the name of the command that was running, the PID, the number of events or the current event counter, and then the name of the event. So in this case it was the really precise cycles on Intel hardware. And then below that you get the instruction pointer and the backtrace. Sadly, you don't have a way yet to configure perf script to also include the name of the file or the line number in the backtrace. I will work on that eventually as well. But right now you could use the instruction pointer address, paste that into editor to line, and it will work. If you want to go further, you can use perf script to generate a shim, like a really tiny Python or Perl script for you that you can then use to build your analysis on. So if you recorded something and then call perf script-g Python, it will generate a Python script for you, and if you run that one, it will be somewhat similar to the normal ASCII output for perf script. But if you look at the sources, you can actually see what's possible there. So you get, in this case, I think I recorded the sys enter and exit events for nanosleep, so any kind of sleeping on Linux. And I get a trace begin and trace end function that will be called at the very beginning, very end of my little script. And then I have little callbacks essentially in my code that will be called for every event. And you can also have catch all, trace point, or sampling event handlers in there. And you get like all the data there. Well, actually it's not all of the data, but the data they thought is useful right now. Some of the stuff is missing, and I really hope to extend the scripting API there. But it's actually pretty simple to write something to measure, for example, the time between different syscalls, and also see different samples that have been running in between with their call stack, and all of these things is possible. And as I said, I used that as the foundation for a really, really tiny call-grain converter script. Let me show you the source code. It is, 150 lines, and most of that is to convert the data to some data structures that can be used at the very end to produce a call-grain data file. So here in trace end, I actually output all the data in the format that I want to have. And here I have the catch all event handler and the catch all trace event handler. And in there I simply add the samples to my data structure, and I can access the call chain and increase the cost and everything, and then output that file. And once that is done, I can open up the resulting file in kcachegrin and it works. So if you wonder how to do that, it's really possible and sometimes worth it, especially if you look into page faults and how they influence your application. So maybe you want to trace page faults and then scheduler events and also CPU cycles and aggregate all of that in one custom application to visualize it all. Okay, cool. Then I think that would be it from my side. If you need any help with that, we offer a training and workshops on that topic as well. So do come visit us. Thank you.